in a row.
All right, we're going to start with questions from homework. Does anybody have any questions from homeworks to this point that we need to talk about? Happy to take a few minutes here at the start and tackle any kinds of questions from homework that we might have. Yeah, Claire.
Okay, so for like question 50 and 49 of the homework, when there's like a crate that has 50 pounds versus like no weight.
Okay. So let's do 50 together. They're basically the same problem, right? Okay. So when I read this, I see a crate weighing 80 pounds is being pulled up a ramp at an angle of elevation of 29 degrees with a force of 130 pounds. And the ramp has an angle of elevation of 22 degrees. And we're asked, what is the amount of force being directed up the ramp? So when I read this, I hear three vectors. So I have a vector from gravity. So like 0, -80. I have a vector from the pull. So that would be like 130 cosine 29, comma 130 sine 29. And then I have a vector from the ramp. Now, we're not told the magnitude for that ramp, so I'll just assume it's 1. So far, so good. So what I'm going to need then, since I'm projecting onto a unit vector, this can just be the projection of G plus P onto R. So I can just do that. Or I guess I'm doing that regardless. But since it's just a unit vector, that's going to be the same thing as the dot product of G plus P and R. So the dot product is just going to be the x components multiplied to, the sum of these x components multiplied by the x component from, it's in the wrong spots. And then the y components added together, so 130 sine 29 plus -80 times sine 22. So that's like what I would do there. So into my calculator we go. Got to make sure I'm in degree mode. Good thing I checked. I switched it out last period. All right. So I have 130 times cosine 29, and then plus 0, so I don't really care about that, times cosine 22 plus 130 sine 29 minus 80 times sine 22. So I get like 9906 for the force. slides. Jacob, pass for you. So again, when I read this, I read, I have gravity, I have pull, and then I have projecting onto, my ramp. And again, since that's a unit vector, the absolute value of that projection vector is really just, well, I guess it's the absolute value of that dot product, but like it was all going to be positive valued anyways. And that's the gist of it. Does that make sense as what to do with the third vector there? Like it feels like there's too much information for two vectors. There was. So there's three going on. But it was nice at least because they had the shortcut available where all I really needed was the dot product and I didn't have to do like actually the projection, which is kind of a hassle. And I think 49 goes similarly. I chose to do 50 intentionally because 49 has the answer that you could check after you tried it yourself, after seeing what to do with three vectors. So that's me trying to help you guys out. Other questions from homeworks? Cool. All right. Well, then for today, we're going to finish up things in Chapter 8. So in Section 4, we're going to be looking at two-dimensional vectors in space. In space. So to do this, we're going to introduce yet another different vector notation. So this we call the IB component form version for a vector, but like when I was a student, we just called this guy a column vector. Still think that's verbiage is used pretty commonly. So instead of writing our component vector horizontally, like wedge A comma B wedge, we're going to write it vertically, parenthesis A on top, B on bottom, parenthesis. The hardest part about this is just breaking the habit of trying to draw a vertical bar in between these. Whenever you write two numbers horizontally, you tend to want to, or vertically, tend to want to make them a fraction. No fraction bar there, but it's like the easiest conversion between forms that you're ever going to see. You guys see what we're doing here? Instead of just writing A comma B horizontally, we're writing A, B vertically. Hey, Mr. Salick, what can I do for you? Sure. All right. So with this new notation, we're going to try to represent lines with vectors. So back when you guys talked about equations for lines, we typically used y equals mx plus b, right? Where our m was the slope. And the way we calculated slope, it was like the change in y coordinates over the change in x coordinates, right? and we said B was like the y-intercept. So that's a point 0, comma B. Always remember that kind of thing. Our vector equation for a line is going to be vector r is equal to vector r naught plus v times t. So just like an equation for a line, our vector equation has a slope, but this time it's a slope vector. That's v, which in the case of our slope would be like the change in x over change in y. Now your first instinct is probably like, Mr. Kulik, what if the slope isn't a fraction? Well, then just write it as a fraction. If it's 3, just write it as 3 over 1. Right? Like, you can take any number and write it as a fraction. No big deal. Everybody's okay with that? Yes?
Why did you add the naught to the r?
That's just that's a symbol we use. So it's different than, so there's not the same variable in the equation. Right? So the r naught is what we call a point vector. So that's just going to be some xy. Where that xy corresponds to any point on our line. So could be the y-intercept, but it doesn't have to be. That being said, it should be clear that there's infinitely many correct answers to write the vector equation for a line. Right? If r naught can be any point on the line, there's infinitely many points on any line, right? So have infinitely many correct answers. Let's do some numeric examples here where we just practice converting back and forth from a slope-intercept equation to a vector line equation, and then from a vector line equation back to a slope-intercept equation. So it says find a possible vector line equation for the line y equals 3x plus 5. Remember, this is just saying a possible because there's infinitely many possible answers here, right? So you just need to find one of them. So to write our vector line equation, we need first our slope vector. To get that, I'm going to recognize the slope for this line is 3. So I can write that as 3 over 1. So my slope vector should be the x, the change in x, so the 1 over the change in y, that's the 3. So it's just the same as the slope, it just flipped upside down. Is that okay? Now, as an aside, if this was like -3, it doesn't matter where you put that negative sign. It could go with the 3, or it could go with the 1. Either way is fine. Just so we're cool with that. There's a negative sign floating around. It doesn't matter what you attach it to, the numerator, denominator, the x or the y in the slope vector. It won't make any difference. Still correct. Cool so far? Okay, my point vector. So again, I know the y-intercept for this is 0, 5, right? So my point vector r0 can just be the vector 0, 5. So my final answer will be vector r equals the vector 0, 5 plus the vector 1, 3 times t. Does that feel okay there? Pretty simple, right? Okay, let's go the reverse direction now. Let's start with the vector line equation, try to recover a slope-intercept equation from that. Yeah. Sure.
Let's see activity.
Okay. Thanks, Paulie. All right. So what we need here is we're going to start by getting the slope. So I know my slope vector is 2, 3. That tells me that my slope should be the change in x, I'm sorry, change in y, which is 3, over change in x, which is 2. Again, it's just the slope vector turned upside down and turned into a fraction. Everybody's okay? And then I have my point vector. That tells me that the point 3, negative 1 is a point on this line. So if I want to write the equation for the line that has slope of 3 halves and contains the point 3, negative 1, I'm just going to treat these guys like an x and y and plug them into the equation along with my slope to find b. So to solve for b, I'm going to need to make a common denominator. Let's go and do that right now. Negative 1, I'm just going to treat as negative 2 over 2. And then when I subtract 9 over 2 from both sides, I get that b is negative 11 over 2. And then all I have to do is put everything back together. And there we are. We've recovered a slope-intercept equation from a vector line equation. This should very much resemble like an Algebra 1 problem where we write the equation for a line given a slope and a point. Right? That should be a familiar problem you've done a bunch of times. You know, you have to do a little bit of work to pull out what the slope and the line or the point are supposed to be, but not very much, right? Not terribly hard to get that the slope was 3 halves and the point was 3, negative 1. Does everybody feel okay so far? Okay. One final idea. So if I give you 2 lines, I know that those 2 lines are either intersecting parallel or coinciding. Coinciding means they are like they overlap, that they're the same line. So lines that intersect have different slopes. As soon as I see the lines have different slopes, I'm going to know that they're intersecting. Parallel lines have the same slope. You should remember that as a property from geometry, or even Algebra 1, it's probably covered. Coinciding lines, well, they're the same line, right? So obviously they have to have the same slope. So what's the difference between parallel lines and coinciding lines? All the points in parallel lines are different, right? They share no points in common. Coinciding lines have all their points in common. Maybe I'll just say no points in common instead of different points. That sounds less specific. Does everybody feel okay with this idea? Again, this should be relatively familiar from like Algebra 1 geometry, even Algebra 2 when you solve systems of equations, you probably talk about this. So if I have two lines like L1 and L2, if I want to sort out whether they're intersecting, parallel, or coinciding, the first thing I'd ask is, do they have the same slope? If the answer is no, we're done and we know they're intersecting. If the answer is yes, we need to check some more. So I'll say, do they have any point in common? If the answer is no, then we're done. We know they're parallel. If the answer is yes, we're also done. We know they're coinciding. Is everybody okay with this as like just a flow chart of what we would do to sort these out? What I'm going to do now is I'm going to redraw this same flow chart, but instead of using the language of lines, I'm going to use the language of vectors and kind of write down how we would do the check for that using our vector line equations. Okay? Does this feel okay? You like this? I hope the visualness of it is usually pretty helpful. So let's say we have vector line equation 1. And then my second vector line equation. So just like before,
is that a comma or a 1?
That's a 1. So it's like V1 and then it's R01. So the first question we ask is, do they have the same slope? The way we check that is, we check if the slope vector for the first line, is it a scalar multiple of the slope vector for the second line? So that'll be a yes or no. And we'll do numeric examples with this in a moment when we're done. If it's no, again, we know they're intersecting. And to find their intersection, we just take the two vector line equations and set them equal to one another. So then we check to see if the answer is yes, they are parallel, or they have the same slope. We need to check if they have a point in common. So what I need to see is if the point vector from the first equation is that on, or is that a point vector on the second equation? So that's what we're checking there. If the answer is no, then we're parallel. If the answer is yes, then we're coinciding. Hi, Jake. Okay, thank you. So what we'll do next is we're just going to do a couple of quick examples of using this flow chart to do this process so you can kind of see what these little vector equation tests that I've written down, what that looks like doing those actually with real numbers involved, what that looks like. Sound good? And that's where we're ending. So we got two examples and we're done. Sound good? Everybody happy? Here we go. So our first example is like, is this intersecting, parallel, or coinciding? So our first vector line equation is this. And our second one is this. So I ask myself, do they have the same slope? So that was basically is V1 times K equal to V2. So again, this is like my R01. This is like my V1, my R02. This is like my V2. So to check this, we're going to say 1, 3 times K and see if that equals 3, 5. Well, if I do the scalar multiplication, basically that first vector becomes K 3K. Is everybody okay with that? I just scalar multiplied the K inside the vector. Hi, Edie.
Okay.
Kirsten, you're going home early. And that implies then that if those two vectors are equal, that k is equal to 3 and 3k is equal to 5. You guys see what we're doing there? They're just like the components have to be equal if the vectors are equal. Well, k equals 3, that one's solved. But if I divide both sides by 3, in the second equation, I have that k is equal to 5/3. Uh-oh, what do you notice? I didn't get the same answer, right? What is that telling you? So no, since those are not the same, that tells us no, they're not the same slope. So that tells us we're intersecting. Okay, so to find that point of intersection, we take R1 and we set that equal to R2. So R1 was the vector 2, 4 plus the vector 1, 3s. We're going to set that equal to the vector negative 1, 5 plus 3, 5 t. Is that okay with where I wrote that vector equation from? Oops. Right? This is just the stuff for R1, and this was just the stuff from R2, right? So what this is saying then, if these two things are equal, 2 plus 1s has to equal negative 1 plus 3t, right? 2 plus 1s equals negative 1 plus 3t. And 4 plus 3s equals 5 plus 5t. Is everybody okay with how I changed that from a vector equation to a system of equations? All right. So now I'm just going to solve this system for S and T. To do that, I could do graphing or substitution or elimination, or what I'm going to do is I'm just going to have my calculator solve it for me, which is what I would recommend you guys to do. You don't have to do it this way, but this is the way I'm going to show you to do it. So I'm going to use a matrix to do that. In order to use a matrix to do this, my system has to be formatted in a specific way. So like the S's have to line up on top of each other, the T's have to line up, the equals has to line up, and then the answers have to line up. So I'm going to start just by rearranging my equation. So in the first equation, I'm going to subtract over the 3t and then subtract over the 2. Is everybody okay with what I did to rearrange that? I subtracted 3t from both sides, and then I subtracted 2 from both sides to get the s and the t on the same side and the constant on the other. I'll do the same thing in the second equation, so I'll subtract 5t from both sides, and then subtract 4 from both sides. Do we feel okay as to what I did there? Okay. Now what I'm going to do is I'm going to enter this into my calculator. So to get this into my calculator, I'm going to press second, and then the X to the -1 button, which is the matrix, opens the matrix menu. If you have your calculator and you want to follow along, feel free. I'll pause for a minute if you're like, ooh, I need to get mine out. If you like, oh, I remember doing this before, I'm good. Fantastic. If you don't and you're like, ooh, I want to follow along, cool. All right, so I press second and the X to the -1 button right now. That's all I've done so far. And now what I'm going to do is I'm going to scroll over to the Edit tab and pick any matrix from here. It doesn't matter. I'm going to just pick matrix A. So my system that I wrote, I have one row and then a second row, one for each equation. So the first dimension here should be 2. So I'll make sure that says 2. And then I have a column for my S's. I have a column for my T's and a column for my answer. So I should have 3 columns. So I should have a 2 by 3 matrix. Second, and then the X to the -1 button. Go to the Edit tab at the top. Use the arrows to move over. Pick a matrix to edit. And then type in 2x3 in the spots. And now what I'm going to do is I'm just going to type in the coefficients of my system exactly like they look on my sheet of paper. So I'm going to write, how did I get a 2 there? Great googly moogly. That's a 1S. Jumpin' Jehoshaphat. Okay. That's better. Who was confused on that? Yeah, I wish you would have spoken up. Woo! All right. Crisis averted there. So I'm going to type in 1, -3, and then -3. And on the bottom, I'm going to type 3, -5, and 1. Is everybody okay with that? Okay. I'm going to now exit out of this menu by pressing second and the mode button. That'll take me back to the main screen. I'm going to go back into my matrix menu now. So second and the X to the -1 button. This time I'm going to go over to the Math tab. And I'm going to scroll down until I find the command RREF. Make sure you pick the one with 2 R's, not 1 R. And I'll press enter. That pastes it onto the home screen. And then I'm going to go back into the matrix menu for the last time. And from the names tab, I'm going to pick that matrix A that we just made, close my parenthesis and press enter. It's on the video. We're going to do another one. Okay. So what this output says now, remember we put the S's in the first column, the T's in the second column, and the answer in the third column, right? So this first line reads 1S plus 0T equals 4.5. Or that just S is equal to 4.5. The second line reads 0S plus 1T equals 2.5. Oh, just T equals 2.5. Is that so far so good? Now I can take either one of these solutions, it doesn't matter which one. I'm going to take the T for sake of argument, and I'm going to take that and plug it back in for T. So I have negative 1, 5 plus, I'm going to do my scalar multiplication. So 3 times 2.5 is 7.5. 5 times 2.5 is 12.5. Everybody's okay there. I just did the scalar multiplication. And then I'm going to add them. So if I add these components, negative 1 plus 7.5 is 6.5. 5 plus 12.5 is 17.5. So that would tell me the solution is at 6.5 comma, or the intersection I should say is at 6.5 comma 17.5. Does that feel okay there? Okay. Let's do another example, and then we'll be finished for today. Sound good? Oops. Okay. So first thing we do is check to see if they have the same slopes. I'm going to stop writing out like the words from the flow chart here on this one. Is that okay? Just going to write out like the work that we're doing. So negative 6k is equal to 1. And then, oops, this 3 down here was supposed to be negative. Sorry. And then 18k equals negative 3. So for the first one, I get k equals negative 1, or 1 over negative 6. For the second one, I get negative 3 over, or k equals negative 3 over 18. And I notice that second fraction can reduce, right? What does 3 over 18 reduce to? 1/6. So I have 1 over negative 6 and then negative 1 over positive 6. Are those still the same thing? Yes, right? Since that's equal, we'll say yes. So we know they're either parallel or coinciding. So now we're going to ask, is there a point in common? So what I'm doing is I'm going to take the point vector from the first equation and see if it's a part of the second equation. So the point vector from R1 is 2, 4. And I want to see if that's a member of R2. So that's 4, 9 plus, what is it, 1, negative 3? Yeah. Everybody good as to how I got that vector equation? I'm going to simplify this side. Well, actually, no, I'm just going to write it as a system. Why bother? So this tells me 2 equals 4 plus 1t. And the second line says 2 equals 9 plus negative 3t. I'm just now going to solve each of these equations for t and see if I get the same result. So in the first equation, I subtract 4 from both sides, and I get t is equal to negative 2. In the second equation, I subtract 9 from both sides, and then divide by negative 3, and I get that t is equal to 5/3. Since these are not equal, that tells me no, they do not share any points. So they must be parallel. That feel okay? Again, not too bad. I think the flow chart really kind of helps in terms of like collecting what it is you're doing and the order that you're doing things. So for next time, your homework from this section is numbers 51 through 54, and then 63 through 66. And then we'll do 73 through 76. So that's not due this Sunday, but the following Sunday. What's due this Sunday would be, what was it? It was like 15 to 50 and the delta math. But I'll give you a little tip here. Mr. Kulik is not going to be checking homework on Monday on his day off. So you might as well just assume it can be due Monday at midnight instead of Sunday at midnight. Hey, take an extra day. I'm not gonna look at anything until I get to school on Tuesday morning, so no big deal. This closes out chapter 8. Next class we'll have our review day, so your half sheet for the test will be due at the end of class next time. If you want to start working on that in advance, you're welcome to do so. I would keep, while you're working on your homeworks, I might take note of what I've been what kind of formulas I had to look up or what kind of problems I would want an example for to do. I'll have a test description up here. I think I just have to import it in. But I want to point out to you at the bottom of the review in the OneNote is a list of the formulas that I will provide to you on the test. So you don't have to worry about putting those on your half sheet. And that's about it for me. How do you guys feel? Things going okay? Not too bad? Okay, let me port over those, the test description. I think I put it in. Yeah, I just forgot to bring it over. And we're just going to copy it. It'll be easier that way. It's a tiny file. So again, this is the test description of the things you'll have to be able to do. So if you're working on your half sheet over the weekend, if you wanted to get an early start on this, these are the kinds of things you'll have to be able to do. I would think that this vector diagram that we made the other class, Francis, thank you for insisting on needing some more explanation, because I think this was probably pretty valuable for everybody. That might be something I would include as it condenses a lot of information in one easy to use place. Yeah, so yeah, I think that's it for me. You guys feel pretty good about what to do and what's the plan and what's going on and how things are going. So next week we have what would it be? Wednesday and Friday, right? So Wednesday would be the review day, Friday would be the test day. Yes, go. Yeah, for sure. No problem.